I wanted to solve a problem that involves potential energy, gravitational potential energy, kinetic energy or moving energy, and energy conservation, and involves changes of energy. In this particular problem, we have a motorbike daredevil. Imagine I'm a motorbike daredevil, and I ride my bike from the launch ramp into the air, and I leave the launch ramp at 35 meters per second speed, and at the highest point I'm traveling at 32 meters per second speed. And based on that information, those two speeds, we're going to calculate the height that I rose to after leaving the launch ramp. So let me start with a little sketch of the problem. So here's my path from the launch ramp to the highest point. My initial speed on this portion of my trajectory is 35 meters per second. My final speed at this highest point on this portion of the trajectory is 32 meters per second. And we're interested in figuring out this vertical distance here. I'll call it the final height minus the initial height, YF minus YI, based on the information given. So that's a picture of the problem, an annotated picture of the problem with the information that we know and with the information that we want. The basic idea here is that during my flight, the total energy is conserved. The total energy of me and the bike when I left the ramp is the same as the total energy of me and the bike at the highest point. What has changed is that kinetic energy that I had at the beginning of my flight has been turned into gravitational potential energy at the highest point of the flight. So I've turned some fraction of that initial kinetic energy into a greater amount of kinetic energy. I can write that down as the change in kinetic energy is equal in size, but opposite in sign to the change in potential energy. Whatever kinetic energy I lost is whatever potential energy I've gained. And then I can just fill in the change in kinetic energy and the change in potential energy in terms of the speed for the kinetic energy and in terms of the height for the potential energy. So change in kinetic energy, that's the final kinetic energy, 1/2 mvf squared, minus the initial kinetic energy, 1/2 mvi squared. And changing gravitational potential energy, that's the final gravitational potential energy, mgyf, minus the initial gravitational potential energy, mgyi. And if we look at that equation, you could probably see here, I can divide through by the mass. So let's cancel out the masses. Each term has a mass in it. And then if I divide through by the acceleration of gravity and multiply by 2, I get that the change in height, final height minus initial height, is equal to the difference in the squares of the initial speed and the final speed divided by 2 times the acceleration of gravity. And so I can just fill in the initial and final speeds. So that's 35 meters per second squared. I won't write in the units here. I'm a little lazy today. 32 meters per second. Again, I won't write in the units. Divided by 2 times 9.8 meters per second squared. And if I carry that calculation out, I've already done it here. I get that the change in elevation is 10.3 meters. And I've computed that from the idea of energy, the forms of energy, potential energy, kinetic energy, and importantly, energy conservation. That energy changed its form from kinetic energy to potential energy, but overall energy was conserved. And so that's an example of working with different forms of energy and energy conservation.